From the silent cosmic dance of distant galaxies to the precise navigation on your smartphone, there's a fundamental fabric weaving through everything we know, yet remaining profoundly enigmatic space-time. It's the stage upon which the entire universe performs a four-dimensional tapestry of three spatial dimensions and one of time. Scientists invoke it constantly: Einstein's theory of space-time, the curvature of space-time, gravitational waves rippling through space-time. It underpins everything from black holes to the Big Bang. Yet despite its omnipresence in our models and technologies, a startling truth remains one that physicists grapple with daily. We fundamentally don't know what space-time is. We use it. We measure its effects. Your GPS wouldn't work without it. We've even photographed its warped structure around black holes and detected ripples propagating through it. But its true nature, that remains one of physics' deepest mysteries. Tonight we'll journey into this profound unknown, exploring why unraveling the essence of space-time could redefine everything we understand about existence itself. Before we dive in, if you're interested in this kind of deep exploration, a quick like or subscribe really helps the channel grow. It makes a huge difference. Now let's begin. Our story, like so many in modern physics, begins in 1905 with a 26-year-old Albert Einstein. Not yet the iconic professor, but a patent clerk in Bern, Switzerland. His days were spent scrutinizing electromagnetic patents, but his nights were dedicated to profound contemplation of the universe. In that single miraculous year, Einstein published 4 papers that would forever reshape physics. One explained Brownian motion, definitively proving the existence of atoms. Another illuminated the photoelectric effect, laying a cornerstone for quantum mechanics. And 2 papers introduced what we now call the special theory of relativity. Special relativity, despite its intimidating name, rests on a surprisingly simple, yet revolutionary idea: the speed of light is constant for all observers, regardless of their own motion. This concept defied centuries of classical intuition. Imagine you're on a train moving at 100 km per hour, and you throw a ball forward at 20 km per hour. An observer on the ground would see the ball travelling at 120 km/h. Velocities simply add up. This is intuitive. It's what we expect from our everyday experience. But Einstein demonstrated that light behaves differently. If you're on a spaceship hurtling at half the speed of light and you shine a flashlight forward, you might expect its light to travel at 1.5 times the speed of light from an external observer's perspective. But no. Light travels at precisely 300,000 kilometers per second, the speed of light for both you on the ship and the observer watching you. Always the same speed. This seems impossible. How can light travel at the same speed for 2 observers when one is already moving at half the speed of light? Einstein's answer was radical space and time adjust themselves to keep the speed of light constant. If you move very fast, time actually slows down for you, relative to a stationary observer. Distances in your direction of motion also contract. These aren't optical illusions. They are verified physical effects. Time and space are not absolute. They are relative, dependent on your motion. The only constant, the only absolute, is the speed of light. This was a seismic shock in 1905, upending centuries of assumptions about the universe. Isaac Newton had built his physics on the bedrock idea that time flowed uniformly for everyone, that a second was a second, no matter your location or speed. Einstein proved that simply isn't true. Time is flexible. Space is flexible. They bend and stretch, depending on your relative motion. Consider the profound implications of this. If humanity could build a spaceship capable of travelling at 90% the speed of light, and you embarked on a journey to a star 10, light years away and back from your perspective on the ship, the journey might only take a few years. Yet upon your return to Earth, 20 years would have passed. Your friends would be 2 decades older. Your children might even be older than you. This isn't science fiction. It's a verified prediction of Einstein's equations. We've tested this phenomenon countless times. Unstable particles in particle accelerators, which normally decay in microseconds, live far longer when accelerated to 99.9% the speed of light. Atomic clocks flown around the world confirm minor but measurable time differences compared to identical clocks on the ground, discrepancies perfectly aligned with Einstein's predictions. The universe lacks a universal now, no cosmic clock ticking uniformly for all. When you speak of something happening right now on a distant exoplanet, that statement holds no absolute meaning. Different observers moving at different speeds will disagree on what constitutes now and which events are simultaneous. Time is not an unyielding river flowing at a constant rate for all. It's more akin to an elastic fabric that stretches and compresses depending on how you traverse it. But Einstein wasn't finished. Special relativity only described objects moving at constant speeds. It didn't account for acceleration or, crucially, gravity. Newton's law of universal gravitation had reigned supreme for over 2 centuries, accurately predicting planetary orbits and the trajectories of cannonballs. Yet Einstein saw its flaw. Newtonian gravity acted instantaneously. If the Sun were to suddenly vanish, Earth, according to Newton, would immediately fly off into space with gravity's influence vanishing across 150 million kilometers of empty space without delay. But Einstein had just shown that nothing could travel faster than light. No signal, no force, no information. If the Sun disappeared, it would take approximately 8 minutes for its light to cease reaching Earth. Einstein realized gravity couldn't operate faster than light either. There had to be a delay. Something had to carry the gravitational influence, and whatever it was, it couldn't exceed the speed of light. This insight led to what Einstein called his happiest thought, which came to him in 1907. Sitting in his patent office contemplating gravity, he imagined a worker falling from a rooftop. As the worker fell, Einstein realized they would feel weightless in freefall. If they dropped a hammer, it would hover beside them, falling at the same rate. They wouldn't see the hammer accelerate away or towards them. It would simply float in their perspective. This concept might seem obvious today thanks to footage of astronauts floating in the International Space Station. But Einstein recognized a profound equivalence. The falling worker and the orbiting astronaut experience the same phenomenon. Both are in free fall. The astronaut isn't truly in zero gravity. They're falling towards Earth just like the worker, but also moving sideways fast enough to continuously miss the planet, constantly falling, yet never hitting the ground. This principle, the equivalence principle, states that freefall is indistinguishable from being in completely gravity-free space, and being in an accelerating rocket is indistinguishable from standing on a planet feeling gravity's pull. You cannot tell the difference inside a windowless room. If acceleration and gravity are equivalent, and special relativity showed that acceleration affects space and time, then gravity must also affect space and time. Gravity must warp space-time itself. The mathematics to describe this, his general theory of relativity, consumed Einstein for another 8 years from 1907 to 1915. He struggled with advanced mathematics he'd never encountered, making errors, publishing incorrect results, and persistently refining his equations. He described the final year as the most exhausting and demanding of his entire career. But in November 1915, he finally unveiled the correct equations. General relativity posits that mass and energy warp spacetime, and objects move through this curved spacetime along curved paths. This is what we perceive as gravity. It's not a force pulling objects together, but rather objects simply following the straightest possible paths through a fundamentally warped geometry. Those paths just happen to appear curved to us because the geometry itself is curved. A classic analogy is a stretched rubber sheet. Place a heavy ball in the center, and it creates a dip. Roll a smaller ball across the sheet, and it curves towards the heavy ball, not because it's pulled, but because the sheet itself is curved. The small ball tries to go straight, but the curved sheet forces it into a curved path. This is precisely what immense masses like the Sun do to spacetime around them. Earth attempting to move in a straight line through space is compelled by the Sun's warped spacetime to follow a curved path its orbit. From Einstein's perspective, there's no pull, just Earth navigating curved spacetime. While the rubber sheet analogy helps, it's also misleading. The sheet is a 2D surface bending in 3D space. Spacetime is 4D, 3 spatial dimensions plus time, and it doesn't bend into some higher dimensional space. It bends into itself. This is incredibly difficult for our brains evolved for 3 spatial dimensions to visualize. Also, the rubber sheet implies an external force, Earth's gravity, pulling the balls down, whereas in real spacetime the curvature itself is gravity. Objects follow geodesics, the straightest possible paths through curved spacetime. A planet orbiting a star is following a geodesic. It perceives itself as moving in a straight line, but the warped space-time makes that straight line curve back on itself, forming an orbit. Einstein's breakthrough culminated in the famous field equations presented on November 25, 1915. These 10 interconnected equations elegantly describe how the distribution of mass and energy determines spacetime's curvature, written compactly as G equals 8pt, where G is the Einstein tensor describing spacetime curvature, and T is the stress-energy tensor describing mass, energy, momentum, and pressure. They are deceptively simple. Solving them for real-world scenarios, however, is immensely challenging. They are nonlinear partial differential equations. The curvature influences mass and energy, which in turn influence curvature, creating a complex feedback loop. Even today, supercomputers run for weeks or months to solve them for scenarios like colliding black holes. General relativity's early successes were spectacular. It perfectly explained the anomalous precession of Mercury's perihelion, a slight shift in its closest approach to the Sun that Newtonian mechanics couldn't account for. The additional curvature of spacetime near the Sun, predicted by Einstein, precisely matched Mercury's peculiar orbit. But the definitive test arrived in 1919. Einstein's theory predicted that gravity would bend light. Specifically, starlight passing near the Sun would be deflected by its warped spacetime, causing stars to appear slightly shifted from their true positions. Such observations are impossible under normal conditions, as the Sun's brilliance obscures nearby stars. However, a total solar eclipse provides a unique window. On May 29, 1919, during a total eclipse, 2 expeditions, one led by Arthur Eddington to Principe Island off West Africa, and another to Sobral, Brazil, photographed stars near the eclipsed Sun. Their measurements confirmed the stars had shifted their light bent precisely as Einstein predicted. The measurements aligned perfectly with his equations. When these results were announced in November 1919, Einstein became an overnight sensation, propelled from respected physicist to the world's most famous scientist. By 1922, the physics community largely agreed Einstein had solved gravity. The theory was complete, or so they thought. Einstein's equations were beautiful but notoriously difficult to work with. Most physicists of the 1920s and 30s could only solve them for very simple cases. One of the earliest and most significant solutions was found by Karl Schwarzschild in 1916. While serving in the German army on the Russian front during World War I, Schwarzschild found time to tackle Einstein's equations. He solved them for the simplest possible scenario, a perfectly spherical non-rotating mass alone in empty space. His solution described space-time curvature around a star or planet. But Schwarzschild noticed something peculiar in the mathematics. At a certain distance from the mass's centre, the equations seemed to break down, yielding infinite values ceasing to make sense. This distance was dubbed the Schwarzschild radius. For our Sun, it's about 3 kilometres. For Earth, about 9 millimetres. These figures seemed nonsensical at the time, as the Sun's 700,000 kilometre radius and Earth's 370 kilometre radius are vastly larger. The strange behaviour appeared deep inside the actual celestial body, where the vacuum solution wasn't applicable anyway. Most physicists, including Einstein, dismissed it as a mathematical quirk. Schwarzschild himself died months after publishing his solution, never knowing its profound implications. For decades, the Schwarzschild radius remained a mere curiosity. Einstein himself strongly disliked the implications. If a mass were compressed beyond its Schwarzschild radius, his equations predicted something truly bizarre. Space-time would warp so intensely that nothing, not even light, could escape. The object would become what we now call a black hole. At its very centre, all the mass would collapse into an infinitesimally small point, a singularity where space-time curvature becomes infinite, and the laws of physics as we know them completely break down. Einstein believed this to be an absurdity, a sign of his theory's limitations, not a prediction of reality. He argued in the 1930s that nature would never permit such an event, believing matter would resist such extreme compression, perhaps through some unknown force pressure or quantum effect, that would prevent collapse beyond the Schwarzschild radius. The singularity he felt was a mathematical artifact, like dividing by zero, not a physical possibility. He believed that the equation was simply being pushed beyond its valid domain. Most physicists agreed. The idea of a star completely collapsing to vanish from the universe seemed preposterous. Stars are held up by pressure-hot gas pushing outwards, balancing gravity's inward pull. When a star exhausts its fuel, it cools, pressure drops, and gravity dominates. But surely some force would halt the collapse, perhaps the degeneracy pressure of electrons as in white dwarfs, or neutrons as in neutron stars. Something had to stop it. Something had to stop. But in 1939, J. Robert Oppenheimer, later famed for leading the Manhattan Project, and his student Hartland Snyder published a groundbreaking paper. They mathematically demonstrated that for an idealized star exhausting its fuel, with no internal pressure left to counteract its own gravity, nothing could halt the collapse. No known pressure or force was strong enough to prevent it once it began. The star would shrink past its Schwarzschild radius and continue to contract until it became a singularity, a point of infinite density where Einstein's equations themselves shatter. Later work confirmed this wasn't just for idealized models. Even with realistic equations describing matter under extreme pressure, sufficiently massive stars would indeed collapse completely. There is a mass limit beyond which no known force can prevent collapse into a black hole. Oppenheimer and Snyder didn't use the term black hole that would be coined by John Wheeler in 1967. They simply described the mathematics of gravitational collapse. But the implications were clear. Einstein's own equations predicted that stars could collapse into objects from which even light could not escape objects, where space-time became so warped it essentially sealed itself off from the rest of the universe. Einstein loathed this outcome. He felt it indicated that general relativity must be incomplete, that something was missing. Yet he could find no error in Oppenheimer's mathematics. The equations were correct. General relativity truly predicted these strange entities. Einstein died in 1955, never fully accepting black holes as real. For the next few decades, most physicists remained skeptical. Black holes seemed too exotic, too extreme, violating our intuitions about how the universe should work. But observations began to accumulate. In the 1960s, astronomers discovered quasars, extraordinarily bright objects in distant galaxies emitting immense amounts of energy from very small regions of space. The only plausible explanation was supermassive black holes, millions or billions of times the sun's mass accreting gas and dust. Matter spiraling into a black hole heats up to millions of degrees, radiating energy before crossing the point of no return. Theorists, meanwhile, made significant strides in understanding what black holes truly implied for physics. In 1965, Roger Penrose proved a remarkable theorem, showing that once a star collapses past a certain point, the formation of a singularity is mathematically inevitable. It wasn't dependent on the star being perfectly spherical or having special properties. Any collapsing star would form a singularity. The laws of physics as described by general relativity effectively mandated it. Stephen Hawking expanded on this work in the late 1960s and early 1970s, working with Penrose and others. He demonstrated that singularities are generic features of general relativity. They don't just appear in black holes. The Big Bang itself, the very beginning of the universe, was a singularity, a point of infinite density and curvature where time itself began. Hawking showed that if you run the universe's expansion backward in time, using Einstein's equations, you inevitably reach a singularity. There's no escaping it within the framework of general relativity. This was profoundly unsettling. General relativity, so spectacularly successful in describing gravity and the motion of objects from planets to galaxies, paradoxically predicted places where it itself broke down. Singularities were like signposts embedded in the mathematics declaring, beyond this point, physics doesn't work. Then in 1974, Hawking made another discovery that sent shockwaves through the physics community. Black holes are not entirely black. They emit radiation now known as Hawking radiation. This arises from a fascinating combination of general relativity and quantum mechanics. Quantum mechanics tells us that empty space isn't truly empty. It's teeming with quantum fluctuations, pairs of particles, and antiparticles spontaneously popping into existence for incredibly brief moments before annihilating each other. These virtual particles exist for such a fleeting time that they cannot be directly observed. They borrow energy from the vacuum, exist momentarily, and then repay it by annihilating. The Heisenberg uncertainty principle allows this provided it happens quickly enough. Near a black hole's event horizon, the point of no return, something else can occur. If a virtual particle pair materializes right at the edge, with one particle appearing just inside the horizon and its partner just outside the particle inside is pulled into the black hole's immense gravity before it can annihilate its partner, the particle outside escapes. To an external observer, it appears the black hole has emitted a real particle. The energy for this real particle comes from the black hole itself. The infalling particle, from the perspective of an outside observer, has negative energy, causing the black hole to lose a tiny bit of mass. The escaping particle carries away positive energy. Over eons, this process causes black holes to slowly evaporate, losing mass. Smaller black holes evaporate faster as their Hawking radiation temperature is inversely proportional to their mass. A solar mass black hole has a temperature of only about 60 nanokelvin, requiring an unimaginable 10^67 years to fully evaporate. But a black hole with the mass of a mountain, about 1 billion tons, would have a temperature of roughly 100 billion Kelvin and would evaporate in a tiny fraction of a second, exploding in a burst of high-energy radiation. This was a revolutionary insight. Black holes are not eternal. They have finite lifespans, eventually evaporating completely into radiation. This led to a new problem that has haunted physics for 50 years, the information paradox. Imagine writing a detailed book full of unique information and then tossing it into a black hole. The book crosses the event horizon, vanishing towards the singularity. From the outside, all that remains of the black hole are its mass, spin and charge, a concept summarized by John Wheeler in the 1970s as "black holes have no hair." You can't tell if a book, a rock or a star fell in. The black hole looks the same. If black holes were eternal, one might argue the information, though inaccessible, remains encoded within. But Hawking radiation changes everything. As the black hole evaporates, it emits thermal radiation, which is inherently random, carrying no information about what created it. You can't examine the heat from a fire and deduce what was burned. This implies the book's information, its words, ideas, the specific arrangement of atoms, is destroyed. This violates a fundamental principle of quantum mechanics called unitarity, which states that information is never truly destroyed. It can be scrambled, dispersed, or hidden in incredibly complex ways, but in principle, it's always recoverable. If you perfectly knew the quantum state of every particle, you could reconstruct the past or predict the future with absolute precision. But Hawking radiation seemed to irrevocably erase information, as if the book had been deleted from the universe's history. This created a profound conflict between general relativity and quantum mechanics. One of them had to be wrong, or our understanding of both was incomplete. Physicists debated this for decades, with Hawking initially arguing that information was indeed lost, breaking quantum mechanics in extreme gravitational fields. Others contended that information must somehow be conserved even if the mechanism was unknown. This unresolved paradox became a glaring signal that something was fundamentally amiss in our understanding of spacetime. Einstein's elegant theory of curved spacetime now predicted regions where physics truly ceased to make sense, where equations broke down, and where black holes might destroy information. Yet this very theory, which seemingly contained the seeds of its own destruction, is one we rely on daily. General relativity isn't just an abstract theory for understanding black holes and the Big Bang. It profoundly impacts your life in concrete, practical ways. Take GPS, the most obvious example. Your phone, your car's navigation system, any device that tells you where you are, relies on a network of satellites orbiting Earth at about 20,000 kilometers. These satellites continuously broadcast signals containing precise timing from their onboard atomic clocks and information about their positions. Your GPS device receives signals from at least 4 satellites, measures the time it takes for those signals to arrive, and uses that information to triangulate your position. The speed of light is constant, so if you know how long a signal takes to arrive, you can calculate the distance to the satellite when it sent the signal. With 4 satellites, you can pinpoint your position in 3 dimensions. Simple geometry. However, there's a catch. The atomic clocks on the satellites don't tick at the same rate as clocks on the ground. 2 relativistic effects are at play. First, the satellites are moving at roughly 14,000 km/h relative to the ground. According to special relativity, time runs slower for moving objects. From the perspective of someone on the ground, the satellite clock should tick slightly slower. This velocity time dilation amounts to about 7 microseconds per day. Second, and more significantly, the satellites are higher in Earth's gravitational field, farther from its centre of mass experiencing weaker gravity. According to general relativity, time runs faster in weaker gravitational fields. This gravitational time dilation causes the satellite clocks to run about 45 microseconds per day faster than ground clocks. Combining these two effects, satellite clocks run approximately 38 microseconds faster per day than ground clocks. This might not sound like much, but light travels about 300 meters in just 1 microsecond. If GPS systems didn't correct for these relativistic effects, your position would drift by about 11 kilometers every single day. Within a few hours, your GPS would be utterly useless, telling you you're in the wrong city. The engineers who designed GPS knew this. They pre-programmed the satellite clocks to tick at a slightly different rate to compensate for relativity. Every GPS calculation implicitly accounts for the curvature of spacetime around Earth. Every time you use GPS to find your way, you're relying on Einstein's equations. You're using general relativity. And it works perfectly. Yet do we understand what spacetime truly is? No, we don't. We just know how to calculate its effects. Here's another even stranger example: gold. Gold is the only metal with that characteristic yellow colour. Silver is silvery white, copper is reddish, iron is grey. Why is gold yellow? The answer lies in relativity. Atoms absorb and emit light at specific frequencies depending on their electron energy levels. For most metals, the light frequencies they absorb are in the ultraviolet range, higher energy than visible light. So they reflect all visible light and appear silver or grey. But gold is different. Gold atoms are heavy with 79 protons in their nucleus, creating a powerful electric field. The innermost electrons move incredibly fast within this strong field, fast enough for relativistic effects to become significant. According to special relativity, as electrons move faster, their mass effectively increases. This alters the spacing between energy levels in the atom. For gold, this relativistic effect shifts the energy levels just enough for gold to absorb blue light instead of ultraviolet. When white light hits gold, the blue frequencies are absorbed and the remaining reflected light appears yellow. Gold's colour is a relativistic effect. Without special relativity, gold would be silvery like most other metals. The same applies to mercury, the only metal liquid at room temperature. Mercury atoms have 80 protons, and their innermost electrons move so fast that relativistic effects weaken the bonds between mercury atoms. The atoms don't hold together as tightly, so mercury melts at a much lower temperature than expected. Without relativity, mercury would be solid at room temperature, and thermometers would be very different instruments. These aren't just oddities. These are real, measurable effects of relativity in everyday materials. The universe we inhabit, the very properties of the elements around us, are shaped by spacetime's curvature and time's flexibility. And we use these effects without ever thinking about them. Consider another example that underlines our reliance on this mysterious fabric, the entire internet, or at least a significant portion of it. Fibre optic cables transmit data as pulses of light, and the timing of these pulses must be incredibly precise. For long-distance fibre optic links, especially for financial transactions where microseconds matter, engineers must factor in relativistic effects. Cables at different altitudes experience slightly different gravitational time dilation. The differences are minute, but in high-speed networks transmitting billions of bits per second, even tiny timing errors accumulate. Corrections based on general relativity are built into synchronization systems. Even more impressively, there's LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO was designed to detect gravitational waves ripples in spacetime, caused by violent cosmic events like colliding black holes or neutron stars. These ripples stretch and compress space as they pass an effect so infinitesimally small that when a gravitational wave traverses Earth, it might alter the distance between 2 points, 4 kilometers apart, by less than 1/10,000th the width of a proton. To put that in perspective, a proton is about 10-15 meters in diameter. 1/10,000th of that is 10-19 meters. LIGO detectors can measure changes in distance that small. If the distance between Earth and the nearest star Proxima Centauri, about 40 trillion kilometers, changed by the width of a human hair, roughly 1/10 of a millimeter, LIGO could detect it. LIGO achieves this by splitting a laser beam, sending 2 halves down 2 perpendicular 4-kilometer tunnels, reflecting them off mirrors at the ends and recombining them. If a gravitational wave passes while the light is travelling, one arm of the detector is stretched ever so slightly while the other is compressed. This creates a tiny shift in the time it takes for light to traverse each arm. When the beams recombine, they produce an interference pattern that reveals the passing wave. The first detection occurred on September 14, 2015, the very first day LIGO began scientific operations after a major upgrade. The signal arrived at the Louisiana detector at 5:51 a.m. Central Time, and 7 milliseconds later at the Washington State detector. The signal lasted about a fifth of a second, starting at about 35 Hz, and rapidly increasing to about 250 Hz, before abruptly cutting off. This pattern was precisely what you'd expect from two black holes spiraling into each other and merging. Analysis showed these were two black holes each about 30 times the mass of the Sun. They had orbited each other for billions of years, slowly spiraling inward as they lost energy to gravitational waves. In the final fraction of a second, they orbited hundreds of times per second, moving at a significant fraction of the speed of light. As they merged, the collision released more energy in that tiny fraction of a second than all the stars in the observable universe emit in the same time frame. Approximately 3 solar masses of energy, equivalent to annihilating 3 suns and converting their entire mass directly into energy, was emitted as gravitational waves in less than a second. That energy propagated outwards at the speed of light as ripples in spacetime. The event occurred 1.3 billion light-years away, meaning the waves took 1.3 billion years to reach Earth. When they arrived, they stretched and compressed LIGO's 4-kilometer arms by about 1,000th, the width of a proton, and LIGO detected it. This discovery, announced on February 11, 2016, confirmed a major prediction of general relativity that had never been directly tested, that accelerating masses produce ripples in space-time that travel at the speed of light. We had seen indirect evidence before through pulsars rapidly spinning neutron stars losing energy at precisely the rate expected if they were emitting gravitational waves. But LIGO was the first direct detection. We literally caught the waves passing through Earth. Since then, LIGO and its sister observatories Virgo in Italy and Kagra in Japan have detected dozens of gravitational wave events, mostly from merging black holes, some from merging neutron stars. Each detection teaches us something new about these extreme objects and the nature of gravity itself. Black hole mergers have revealed a surprising population of intermediate mass black holes, objects ranging from 30 to 100 solar masses. Before LIGO, we knew about stellar mass black holes forming from individual stars, typically 5 to 20 solar masses, and supermassive black holes at galactic centers, millions to billions of solar masses. The gap in between was a mystery. LIGO found that gap being filled by black holes, suggesting formation mechanisms we don't yet fully understand. We've also learned about the spin of black holes. When two black holes merge, they often spin. Sometimes their spins align, sometimes they're misaligned, which tells us about how the black holes formed. Binary black holes forming together from a stellar pair should have aligned spins. Those forming separately and then gravitationally capturing each other should have random spin orientations. LIGO data suggests both types exist. In August 2017, LIGO and Virgo detected gravitational waves from two merging neutron stars about 130 million light-years from Earth. This event was particularly special because neutron star mergers also produce light. Unlike black holes, which are inherently dark, neutron stars are made of ordinary matter and glow. When they merge, they produce a brilliant explosion called a kilonova. Within seconds of the gravitational wave detection, LIGO sent alerts to astronomers worldwide. Telescopes immediately turned to the patch of sky where the signal originated. Within hours, they found it a new point of light in the galaxy NGC 40993. Over the following days and weeks, dozens of telescopes observed the kilonova across different wavelengths from gamma rays to radio waves. This was humanity's first observation of a cosmic event with both gravitational waves and light, the dawn of multi-messenger astronomy. The observations confirmed something physicists had long suspected: heavy elements like gold, platinum, and uranium are forged in neutron star mergers. The collision creates conditions so extreme that atomic nuclei are slammed together and built up into heavier elements. The kilonova ejected about 1/100th of a solar mass of material, much of it gold and platinum. All the gold on Earth, every gold ring, every gold coin, every bar in bank vaults was forged in neutron star mergers billions of years before our solar system formed. The gold was scattered into space mixed with gas and dust and eventually incorporated into the disk of material that formed the sun and planets. When you wear a gold ring, you're wearing atoms forged in the cataclysmic collision of neutron stars. Every gravitational wave detection is direct proof that spacetime is real, that it can be warped and rippled, that Einstein was right. We are not just inferring spacetime's existence from theoretical arguments, we are directly measuring it. We are watching it jiggle. Yet detecting gravitational waves doesn't tell us what spacetime is made of. It only confirms its existence, and that it behaves the way Einstein's equations describe. It's like detecting sound waves travelling through air. You can measure the waves, study their properties, use them for communication and music. But measuring sound waves doesn't tell you what air is made of. You need other experiments to discover molecules and atoms. Similarly, measuring gravitational waves tells us spacetime can vibrate, but it doesn't tell us what the vibrating fabric itself actually is. That remains a mystery. And then there are the black hole images. In April 2019, the Event Horizon Telescope collaboration unveiled the first ever image of a black hole. It wasn't a photograph in the traditional sense. It was radio telescope data from observatories across the globe combined using a technique called very long baseline interferometry. 8 radio telescopes spread across the planet from Hawaii to Antarctica, from Spain to Chile, all aimed at the same target simultaneously. They recorded radio waves at a wavelength of 1.3 millimeters of frequency, at which the gas around black holes glows brightly. The technique works by combining signals from all the telescopes as if they were parts of a single telescope the size of Earth. The resolution you can achieve with a telescope depends on its size. Larger telescopes can see finer details. By spreading telescopes across the planet and combining their signals, you can achieve a resolution equivalent to a telescope about 13,000 kilometers wide. That resolution is enough to read a newspaper in New York from a cafe in Paris, or to see an orange lying on the surface of the moon. The process is incredibly difficult. You need atomic clocks at each telescope to precisely timestamp when each signal arrives. You need to record petabytes of data so much that it cannot be sent over the internet. Hard drives have to be physically shipped to a central facility for processing. You need to correct for Earth's rotation atmospheric effects the motion of the telescopes. And you need to do all this for signals coming from billions or trillions of kilometers away, signals so faint they are almost lost in the noise. The result was an image showing a bright ring around a dark circle. The black hole lies at the center of the galaxy Messier 87, about 55 million light-years from Earth. The black hole itself is about 6.5 billion times the mass of the Sun. The dark region in the center of the image, the shadow, is about 40 billion kilometers across, roughly 3 times the size of Pluto's orbit around the Sun, and it is utterly dark because that is the event horizon. No light escapes from within. The bright ring around the shadow is gas spiraling around the black hole at nearly the speed of light. The gas is heated to billions of degrees by friction and magnetic fields glowing in X-rays, visible light and radio waves. The light we see in the image has been bent by the extreme curvature of space-time around the black hole. Some photons orbit the black hole multiple times before escaping. Some are bent just enough to reach our telescopes. The bright ring appears brighter on one side because the gas is rotating. On one side it's moving toward us, and relativistic effects make it appear brighter. On the other side it's moving away, and it appears dimmer. What you're seeing in that image isn't the black hole itself. The black hole is the dark circle in the center, the region from which no light escapes. What you are seeing are the effects of the black hole on the space-time around it. Light from the hot gas is being bent, twisted, focused by the curved space-time. The image is a direct photograph of Einstein's predictions realized. The size of the shadow, the shape of the ring, the distribution of brightness all match computer simulations based on general relativity. In May 2022, the collaboration released an image of a second black hole. This one is at the center of our own galaxy, Sagittarius A. It's about 4 million times the mass of the Sun, much smaller than the Messier 87 black hole, but it's much closer, only about 27,000 light-years away instead of 55 million. Again, the image shows a bright ring around a dark shadow. You're looking at curved space-time. You're seeing photons that have been bent by gravity on their journey to Earth. These images required some of the most sophisticated data processing ever undertaken in astronomy. The raw data from the telescopes doesn't directly show an image. It shows correlations between signals at different telescopes. To turn this into an image, you need to run algorithms that essentially solve an inverse problem. Given these correlations, what image would have produced them? There are many images that could fit the data, so the algorithms incorporate assumptions about what images are likely based on physics and prior knowledge. The final image is the one that best fits the data while satisfying those physical constraints. The amazing thing is that different teams using different algorithms and different assumptions all produced very similar images. The bright ring is real. The shadow is real. You're looking at light bent by gravity. These images are literal photographs of Einstein's predictions come to life. They are not artists' renditions or computer simulations. They are images constructed from actual data. Photons that have travelled from the edge of an event horizon across millions or tens of thousands of light years to reach Earth. We use this idea every day in GPS in the colour of gold, in the liquidity of mercury and fibre optic networks, in gravitational wave detectors in black hole images. We have built entire technologies based on Einstein's framework, and that is both astounding and unsettling. It's like discovering that your house rests on an invisible foundation. You can measure how it responds to weight. You can calculate how it bends under pressure. You can predict how it will behave. But the material itself remains unknown, so let's delve into this mystery. What precisely don't we understand about space-time? The answer isn't simple, but it can be broken down into three big questions. Three frontiers where our knowledge falters. Three riddles that, if solved, would revolutionize physics and perhaps technology. What is space-time made of? Let's start with the most fundamental question. What is space-time? Einstein's equations describe how space-time curves in response to mass and energy. They tell us how to calculate the curvature given the distribution of matter. They predict how objects move through curved space-time, but they don't tell us what space-time actually is. In Einstein's theory, space-time is treated as a smooth continuum. You can zoom in on any point in space and there's always more space at smaller scales. You can divide time into smaller and smaller intervals, and there's always more time. Space and time are continuous, infinitely divisible. This works perfectly for calculations at the scales we can observe, but there's reason to believe this can't be the whole story. Quantum mechanics. The theory describing particle behavior at very small scales dictates that almost everything in nature is discrete quantized, appearing in indivisible packets rather than as a continuum. Energy comes in quanta, light comes in photons, even an electron spin takes on discrete values. You can't have half a photon or an electron spinning at an arbitrary angle. The quantum world is fundamentally grainy, not smooth. This suggests that space and time themselves might also be quantized at very tiny scales. There might be a smallest possible length, a quantum of space. There might be a smallest possible interval of time, a quantum of time. Below these scales, it wouldn't make sense to speak of smaller distances or shorter times. Space and time would be fundamentally discrete, like a digital photograph made of pixels rather than a continuous analog image. This scale is called the Planck length, approximately 10 lawach or 35 meters. To grasp its minuteness, a proton is about 10 diam, 15 meters in diameter. The Planck length is 20 orders of magnitude smaller than a proton. If you magnified a proton to the size of the observable universe, the Planck length would be the size of a tree. At this scale, quantum effects on spacetime itself would become important. The smooth spacetime fabric Einstein described would break down into something else, something grainy, something chaotic. Physicists call this quantum foam. The idea is that if you could zoom in, far enough spacetime would look turbulent, bubbling with quantum fluctuations, constantly forming and dissolving tiny structures. But we have no direct way to probe these scales. The Planck length is so tiny that we cannot build experiments to measure it. The energy required to probe Planck scale physics would be approximately 1019 giga-electron volts. The Large Hadron Collider, the most powerful particle accelerator ever built, reaches energies of about 14,000 giga-electron volts. To probe the Planck scale, you would need an accelerator about 10,000 trillion times more powerful. That's far beyond anything we can build with foreseeable technology. So we're stuck trying to figure out what happens at these scales using pure theory mathematics and indirect reasoning. And there are several competing ideas, none of which we can directly test. One leading contender is loop quantum gravity. This approach takes Einstein's equations and attempts to quantize them directly. Instead of viewing spacetime as a smooth continuum, loop quantum gravity posits that spacetime is made of discrete chunks connected in a network. Space is woven from loops, tiny spacetime loops about the size of the Planck length. These loops connect to form a network, and the geometry of spacetime emerges from how these loops are arranged and connected. In this picture, area and volume are quantized. You can't have an arbitrary area or volume. They come in discrete units, multiples of the Planck length squared or cubed. Spacetime has a smallest possible volume, and you cannot divide it further. This resolves some problems. It suggests that singularities might not actually exist at the center of black holes or at the Big Bang. Instead of collapsing into an infinitely small point, matter would collapse into a minimum volume determined by quantum effects. The singularity would be replaced by a quantum bounce or some other structure. But loop quantum gravity has its own challenges. It's mathematically complex and difficult to extract testable predictions. It also hasn't been successfully unified with the other forces of nature or with quantum field theory, the framework describing how particles interact. It is a theory of quantum gravity, but it's not clear how to incorporate the electromagnetic force, the weak nuclear force, or the strong nuclear force into the same framework. Another prominent approach is string theory. String theory proposes that the fundamental objects in nature are not point particles, but tiny vibrating strings. Different vibrations of these strings correspond to different particles. An electron is one vibration, a photon is another, a quark another, and a specific vibration corresponds to the graviton, the hypothetical quantum particle that would carry the gravitational force. In string theory, space-time emerges from the interactions of these strings. The strings exist in a higher dimensional space, typically 10 or 11 dimensions rather than the 4 dimensions we experience. The extra dimensions are compactified, curled up so small that we don't perceive them compressed at scales near the Planck length. The geometry of space-time, the curvature we experience as gravity, arises from how these strings move and interact within this higher dimensional space. String theory is elegant in many ways. It naturally incorporates gravity. Unlike other attempts to quantize gravity that run into mathematical inconsistencies, string theory is mathematically consistent. It unifies all the forces, electromagnetism, the weak nuclear force, the strong nuclear force, and gravity, all emerge from the same framework, from strings vibrating in different ways. It has a rich mathematical structure that is deeply connected to advanced mathematics. Mathematicians have discovered new theorems and connections in pure mathematics by studying string theory. String theory emerged in the 1970s initially as an attempt to describe the strong nuclear force, though it ultimately failed in that endeavour. However, physicists realised that the theory naturally contained a description of gravity. In the 1980s and 90s, string theory underwent rapid development. Physicists discovered that there were actually 5 different versions of string theory, all mathematically consistent yet ostensibly distinct. This was perplexing. If string theory was the fundamental theory of nature, there should only be one version. Then, in 1995, Edward Witten proposed that all 5 versions were actually different limits of a single, more fundamental theory, which he called M-theory. M-theory operates in 11 dimensions. The 5 string theories are different ways of looking at this same underlying theory. This grand unification suggested that string theory might indeed be unique. String theory also made specific predictions about physics beyond the standard model. It predicted supersymmetry, a hypothetical symmetry, relating particles with different spins. For every known particle, there should be a superpartner. An electron would have a selectron, quarks would have squarks, photons would have photinos. If supersymmetry exists, it would resolve several problems in particle physics and provide a natural candidate for dark matter. But here's the rub: we have searched extensively for superparticles at the Large Hadron Collider and have found none. The LHC has probed energies up to about 14,000 giga-electron volts, producing collisions energetic enough for superparticles to have been created if they existed at accessible energies, but we haven't seen them. This doesn't entirely rule out supersymmetry. The particles could be heavier than we can currently create, but it's certainly disappointing. String theory led us to expect supersymmetry at energies we could reach, and it wasn't there. String theory also suffers from another severe problem: There's an enormous number of possible string theories depending on how you compactify the extra dimensions. The 6 or 7 extra dimensions can be curled up in a staggering variety of ways, each yielding a different 4-dimensional theory with different particles and forces. Current estimates suggest there could be 10,500 different versions, possibly more. This is known as the landscape problem. 10,500 is an inconceivably vast number, far greater than the number of atoms in the observable universe, roughly 1080. With 10,500 possible string theories, how do we know which one describes our universe? There's no principle within string theory that picks one vacuum state over another. Some physicists have argued that perhaps all these vacuum states are real, that each describes a different universe in a vast multiverse. Our universe just happens to be a particular point in this landscape. We exist in this specific universe because its physical constants happen to allow for the formation of stars, planets, and life. This anthropic reasoning is unsettling for many physicists. It seems to abandon the goal of explaining why the laws of physics take on their specific form. Instead, it suggests the laws are essentially random, varying across different universes, and we simply inhabit one of the rare universes where the laws permit life. That isn't a satisfying explanation. It doesn't predict anything. It can't be tested. You can't observe other universes forever beyond our cosmic horizon. And there's an even more fundamental problem with string theory. It offers almost no testable predictions at energies we can reach with current or foreseeable technology. The natural scale of string theory is the Planck energy, about 1019 giga-electron volts. The LHC reaches energies of about 10⁴ giga-electron volts. To probe the Planck scale directly, we would need an accelerator 10,000 trillion times more powerful than the LHC. Building such a machine is far beyond our technological capabilities. It might even be beyond the capabilities of any civilization bound by the laws of physics as we understand them. Without testable predictions, how do we know string theory is true? It is mathematically beautiful. It is logically consistent. It unifies the forces elegantly. But beauty and elegance are not evidence of truth. History is replete with beautiful theories that turned out to be wrong. Physics demands experimental verification. We need to test theories against reality. And for string theory, that is incredibly difficult, perhaps impossible. Some physicists argue that string theory has become more of a mathematical framework than a physical theory. It has generated profound insights into mathematics and theoretical physics. It has given us tools to perform calculations in quantum field theory. It has revealed deep connections between disparate areas of physics and mathematics. But as a theory of fundamental reality, as a theory of quantum gravity that explains what spacetime truly is, it remains unproven. It could be a beautiful mathematical construct that has nothing to do with how the universe actually works. There's also a more radical idea that has gained traction. In recent years, perhaps, spacetime isn't fundamental at all. Perhaps space and time are emergent properties of something deeper, something not at all like space or time. This is the idea behind approaches like EREPR, named after Einstein-Rosen, Bridges wormholes, and Einstein-Podolsky-Rosen entanglement. The basic idea is this quantum mechanics allows for a strange phenomenon called entanglement. Two particles can be entangled such that measuring one instantly influences the other, regardless of how far apart they are. This isn't faster-than-light communication, as you can't control your measurement outcome, but it's a correlation that exists across space without anything travelling through space between them. In 1935, Einstein and Nathan Rosen also wrote a paper about solutions to general relativity that contained wormholes, shortcuts through spacetime connecting distant regions. These were called Einstein-Rosen bridges, but the wormholes in their solutions were unstable. They would collapse before anything could pass through them. In recent years, physicists have wondered if there might be a connection between entanglement and wormholes. The idea is encapsulated by the equation ER-EPR, where ER stands for Einstein-Rosen bridges, and EPR stands for Einstein-Podolsky-Rosen entanglement. The proposal is that when two particles are entangled, they are connected by a tiny wormhole, a thread of spacetime linking them. If this is true, it means that spacetime itself is woven from entanglement. The connections between distant points in space, the very geometry that we think of as spacetime, would emerge from quantum correlations between particles. Space would be an illusion, a useful way to describe something more fundamental. Distance would emerge from the pattern of entanglement, This is speculative. It is not a complete theory, but it is motivated by serious theoretical work and by discoveries about the nature of black holes and entanglement. And it points to a possibility that is both exciting and unsettling. Everything we think we know about space and time might be wrong at a fundamental level. They might not be the basic building blocks of reality. They might be emergent properties only appearing at large scales, just as the temperature and pressure of a gas emerge from the motion of individual molecules. The bottom line is this: we don't know what space-time is made of. We have equations that describe how it behaves. We can measure its curvature. We can detect waves travelling through it. But the fundamental nature of the fabric itself remains a profound mystery. Now let's move to the second big question: what happened at the Big Bang? When we run the universe's expansion backward in time using Einstein's equations, we inevitably reach a point where the entire universe is compressed into an infinitesimally small, infinitely dense singularity. This is called the Big Bang singularity. It's the beginning of time, the birth of space matter and energy all at once. But calling it a singularity is just another way of saying the equations break down. At the singularity density becomes infinite, temperature becomes infinite, the curvature of space-time becomes infinite. Anything divided by zero or multiplied by infinity yields nonsense. The mathematics stops working, and that means we don't actually know what happened. We have very good evidence for the Big Bang in the general sense. The universe is expanding. We can measure the expansion. We can see galaxies moving away from us in all directions. And when we measure the light from distant galaxies, we see that it's redshifted. The wavelengths are stretched out because the space between us and those galaxies has expanded while the light was travelling towards us. The farther away a galaxy is, the more its light is redshifted, meaning it's moving away from us faster. This relationship was discovered by Edwin Hubble in 1929, and it's one of the foundational observations of cosmology. If the universe is expanding now, it must have been smaller in the past. Run the clock backward and everything gets closer together. The temperature and density increase. Eventually you reach a point about 13.8 billion years ago, when the universe was incredibly hot and dense. We call this the Big Bang, but that's a bit misleading. It wasn't an explosion in space, it was the expansion of space itself. We also have another crucial piece of evidence. In 1964, Arno Penzias and Robert Wilson discovered the cosmic microwave background CMB radiation. Working at Bell Labs in New Jersey, with a large horn antenna built for satellite communication, they were trying to measure radio signals from the Milky Way but kept detecting an annoying background noise that wouldn't go away. No matter which direction they pointed the antenna, no matter the time of day or night, the noise was always there. Initially, they thought it might be interference from New York City, but the signal had the same intensity from all directions. They thought it might be heat from the ground or atmosphere, but the signal had the wrong spectrum for thermal emission from Earth. They even suspected pigeon droppings in the antenna and meticulously cleaned it, removing what they politely called white dielectric material. But the signal persisted. Eventually they learned that theoretical physicists at Princeton, just a few miles away, had accurately predicted exactly such a signal. If the universe began in a hot, dense state and expanded and cooled, there had to be residual radiation from that initial hot phase. The radiation would be stretched by the expansion of the universe from high-energy gamma rays down to microwave frequencies, and it had to come from every direction uniformly, because the early universe was nearly uniform everywhere. Penzias and Wilson had accidentally discovered the smoking gun evidence for the Big Bang. The CMB is the leftover light from when the universe was only about 380,000 years old. Before that time, the universe was too hot for atoms to form. Temperatures exceeded 3000 Kelvin. At such temperatures, electrons had enough energy to escape atomic nuclei. Electrons and protons existed separately as a hot plasma. In this plasma state, light couldn't travel far. Photons would constantly scatter off free electrons, bouncing from one electron to another like a ball in a pinball machine. The universe was opaque, like being inside a dense fog or a cloud. You couldn't see through it because light was constantly absorbed and re-emitted by the plasma. But as the universe expanded and cooled, the temperature eventually dropped below 3000 Kelvin. At this point, electrons and protons could combine to form neutral hydrogen atoms, a process called recombination, which happened rather suddenly throughout the universe. Suddenly light could travel freely, the universe became transparent. Photons could stream through space without scattering. Those photons have been travelling ever since. They have been stretched by the expansion of the universe from visible light, with wavelengths of about 500 nanometers, to microwave radiation, with wavelengths of about 2 millimeters. The redshift factor is about 100. The universe has expanded by a factor of 100 since recombination. We can detect this radiation today coming from every direction in the sky. It's a nearly uniform glow, with a temperature of about 2.725 Kelvin, just a few degrees above absolute zero, but it's not perfectly uniform. There are tiny variations, minute differences in temperature from one direction to another. Some regions are slightly warmer, about 2.7255 Kelvin. Some are slightly cooler, about 2.7245 Kelvin. The variations are only about 1 part in 100,000, incredibly small, but they are real and profoundly important. These variations are the seeds of structure in the universe. The slightly denser regions had slightly higher temperatures. These regions had slightly stronger gravity. Over billions of years, matter was pulled into these slightly denser regions by gravity. Denser regions became denser. Less dense regions became emptier. Over time, those tiny variations grew into the galaxies, galaxy clusters, and superclusters we see today. Every galaxy, every star, every planet, including Earth, exists because of these minuscule quantum fluctuations in the early universe that left their imprint on the cosmic microwave background. We have mapped these temperature variations with incredible precision using satellites. The COBE satellite in the early 1990s made the first detections. The WMAP satellite from 2001 to 2010 mapped the sky at much higher resolution. The Planck satellite from 2009 to 2013 produced the most detailed maps measuring temperature variations across the entire sky with a resolution of about 5 arc minutes, roughly a sixth the width of the full moon. From these maps, we can deduce the fundamental properties of the universe, its current age of 13. 8 billion years, its composition about 5% ordinary matter like atoms, about 27% dark matter, which we can't see directly but has gravitational effects, and about 68% dark energy, which is causing the expansion to accelerate. The geometry of space, it appears to be flat, meaning parallel lines will forever remain parallel, neither converging nor diverging. And the rate of expansion, the Hubble constant, which tells us how fast galaxies are receding from one another. All of this comes from studying tiny temperature variations in ancient light. The CMB is one of the most compelling pieces of evidence for the Big Bang. It's a baby picture of the universe, and it matches the predictions of Big Bang cosmology with astounding accuracy. We can calculate what the temperature variation should look like based on our theories of how the early universe evolved, run computer simulations, and compare them to observations. The agreement is exceptionally good. Modern cosmology can explain the patterns we see with greater than 1% accuracy. But when we try to understand the very beginning, the first few moments, we hit a wall. Einstein's equations predict a singularity. But singularities are where the theory breaks down. At the Planck time, about 10 to the 43, seconds after the Big Bang, quantum effects on spacetime would have become crucial. Below this timescale, general relativity cannot be trusted. We need a theory of quantum gravity, and we don't have one. The best we can do is patch the problem with a theory called cosmic inflation. Inflation was proposed in the early 1980s by Alan Guth and others. The idea is that in the very early universe there was a brief period when space expanded exponentially. In a tiny fraction of a second, the universe grew by a factor of at least 10 to the 26. A region smaller than a proton inflated to the size of a grapefruit or larger. This solves several problems. It explains why the universe looks so uniform in all directions. Regions of space now billions of light years apart were once close enough to interact and reach the same temperature. It explains why space appears flat rather than curved. Any initial curvature would have been stretched away by the rapid expansion, much like the surface of a balloon looks flatter as you inflate it. And it explains the origin of structure. Quantum fluctuations during inflation would have been stretched to cosmic scales, creating the tiny density variations we see in the cosmic microwave background. Inflation is supported by observations. The patterns in the CMB match the predictions of inflation. But inflation doesn't solve the singularity problem. It merely pushes it back. Inflation requires very specific initial conditions. You need a particular type of energy field to drive the expansion, and you need the universe to start in a special state for inflation to work. Where did those conditions come from? We don't know, and if you run inflation backward far enough, you still hit a singularity where the equations break down. Some physicists have proposed alternatives. One idea is that the Big Bang wasn't the beginning. Perhaps the universe bounced. Maybe it was contracting before the Big Bang and then bounced at a minimum size, transitioning from contraction to expansion. This would require quantum effects to prevent the collapse before it reached a singularity, creating a quantum bounce. Loop quantum gravity suggests this might be possible, but the mathematics is not yet complete. Another idea is that the universe didn't start from a singularity at all, but emerged from nothingness through a quantum process. This delves into deep philosophical territory about what nothingness even means. In quantum mechanics, empty space isn't truly empty. It's filled with quantum fluctuations, virtual particles popping in and out of existence. Some models suggest that the universe might have emerged from a quantum fluctuation of the vacuum, a spontaneous creation event allowed by quantum mechanics. But all these ideas are speculative. We don't have a complete theory describing the universe's origin. We don't know what happened at the Big Bang singularity or if there even was a true singularity. General relativity's equations point to a beginning, but they also tell us that they cannot be trusted at that very beginning. It's like a map that shows you how to get somewhere, but there's a blank space at the destination labelled "Here be dragons." There's also the possibility of eternal inflation. Some versions of inflationary theory suggest that once inflation starts, it never completely stops. Different regions of space stop inflating at different times, creating pocket universes, separate domains with their own physical properties. Our observable universe would just be one pocket in an eternally inflating multiverse. This is a bold idea with profound implications, but it's also very difficult to test. If other pocket universes are forever beyond our cosmic horizon, we can never directly observe them. The question of what happened at the Big Bang remains one of physics' deepest mysteries. We know the universe had a beginning. We know it was once incredibly hot and dense. We know it has been expanding for 13.8 billion years. But the very first moment, the nature of that beginning is obscured behind a wall of ignorance. We need a theory of quantum gravity to go further, and we don't have one. Do black holes destroy information? The third big question brings us back to black holes and the information paradox. Does a black hole destroy information? This might sound like an abstract philosophical question, but it touches on the core of how the universe operates at its deepest level. In quantum mechanics, the evolution of a quantum system is described by the Schrödinger equation. This equation is deterministic. If you know the quantum state of a system at one time, you can calculate its state at any other time, past or future. Information is conserved. The quantum state carries a complete description of the system, and that information never vanishes. It can be scrambled, diffused among many particles in complex ways, but in principle it's always there. This is called unitarity, and it's a fundamental principle of quantum mechanics. Processes are reversible. If you know the final state perfectly, and you run the equations backward, you can reconstruct the initial state. Information is never lost. But Hawking radiation seems to violate this. As a black hole evaporates, it emits thermal radiation that carries no information about what fell in. Thermal radiation is characterized only by its temperature. It is random. If you collect all the Hawking radiation from an evaporated black hole, you cannot reconstruct what went in. The information is lost. To be more concrete, imagine writing a book and tossing it into a black hole. The book contains information, the specific arrangement of words on each page, the precise positions of all the atoms making up the paper and ink. In principle, if you knew the book's quantum state perfectly, you could describe it with absolute precision. Now the book crosses the event horizon and falls toward the singularity. From the outside, the black hole has increased its mass slightly by the mass of the book, but you cannot tell what fell in. The black hole carries no trace of the words on the pages. Now wait. The black hole slowly evaporates via Hawking radiation. After a very long time, much longer than the current age of the universe, for a sizable black hole, the black hole vanishes completely. All that's left is a cloud of photons and other particles, random thermal radiation. Can you reconstruct the book from this radiation? According to Hawking's calculations, no. The information is lost. The words are gone forever. This created a paradox. Either quantum mechanics is wrong, and information can be destroyed, or general relativity is wrong, and black holes don't actually destroy information, or both theories are incomplete and something else is happening that we don't understand. For decades, physicists debated this. Hawking argued that information was indeed lost, that quantum mechanics broke down in extreme gravitational fields. Others, including Leonard Susskind and Gerard 't Hooft, argued that information must be conserved, that we simply hadn't understood the mechanism. The debate was fierce, often called the Black Hole Wars. A crucial insight came from the holographic principle. This is the idea that all information about what's inside a black hole is somehow encoded on its event horizon, the surface marking the point of no return. The area of the event horizon is proportional to the black hole's entropy, a measure of how much information it contains. This suggests that information isn't lost inside the black hole, but is stored in a scrambled form on its surface. The holographic principle was inspired by the work of Jacob Bekenstein and Stephen Hawking on black hole thermodynamics. They showed that black holes have an entropy proportional to the area of their event horizon, not their volume. This was peculiar. For ordinary objects, entropy is proportional to volume. A larger box can hold more information, but for black holes it's the surface area that matters. This suggested that the information content of a region of space might be determined by that region's boundary, not its interior. This idea has been extended to a more general principle. The holographic principle states that all information in a volume of space can be encoded on that volume's boundary. The universe might be like a hologram, where the 3D world we experience emerges from information encoded on a 2D surface. String theory provides some support for this. In some models, there's a mathematical correspondence between a theory of gravity in higher dimensional space and a gravity-free quantum field theory on that space's boundary. This is called the ADS-CFT correspondence, and it's one of the most important discoveries in theoretical physics in the last 30 years. It suggests that gravity and space-time might be emergent properties arising from a more fundamental quantum theory that doesn't include space and time as fundamental ingredients. But even with the holographic principle, the information paradox wasn't entirely resolved. The question remained, how precisely does the information escape the black hole? Hawking radiation is thermal. It's random. How can it carry information? In recent years, there has been a breakthrough. A crucial development came from thinking more carefully about what happens to entanglement as a black hole evaporates. As Hawking radiation is emitted, the escaping particles are entangled with particles falling into the black hole. This creates correlations between the inside and outside of the black hole. As the black hole evaporates, these correlations change in complex ways. In 2019 and 2020, a series of papers introduced the concept of quantum extremal surfaces and islands. The idea is that when you calculate the entropy of Hawking radiation, you need to include contributions not just from the radiation itself, but also from a region inside the black hole, an island that is correlated with the radiation. As the black hole evaporates, this island grows. Eventually it encompasses the entire interior of the black hole. At this point, the radiation carries all the information that fell in. The information is conserved. This finally led to a solution to the Page curve problem. Don Page calculated in the 1990s that if information were conserved, the entropy of Hawking radiation would initially increase as the black hole evaporated, but then decrease back to zero as the last remnants of the black hole vanished. This is because in the early stages of evaporation, radiation is being emitted and carrying away entropy, but in the later stages of evaporation, as more and more information escapes, the entropy would decrease. The radiation would become increasingly correlated with what went in. For decades, no one could explain how this Page curve could emerge from the physics of black holes. But the recent work on islands shows that the Page curve emerges naturally when you carefully perform the calculations. The entropy of the radiation follows precisely the curve Page predicted. Information is conserved. Does this mean the information paradox is solved? Most physicists believe we're very close, but some details still need to be worked out. The island calculations work in simplified models, but haven't been fully proven for realistic black holes in our 4D universe. There are also deeper questions about what it means for information to be encoded in Hawking radiation in such a complex way. Can the information truly be extracted in practice, or is it so thoroughly scrambled that it is effectively lost even if it is technically still there? But the progress is real. The black hole information paradox, which seemed an intractable conflict between quantum mechanics and general relativity, is slowly yielding to new ideas and new mathematics. And those new ideas point to something profound: space-time, and gravity may not be fundamental. They may emerge from quantum entanglement. The fabric of space-time is woven from quantum correlations, and when we fully understand that connection, we will have a theory of quantum gravity. So why does all this matter? Why should you care what space-time is made of, whether it's loops or strings or entanglement? Why does what happened at the Big Bang, or whether black holes destroy information, matter? These questions seem abstract and far removed from daily life, but solving these mysteries could change everything. First, understanding space-time at a fundamental level would complete the picture of reality that physics has been building for centuries. Currently, we have two grand theories. General relativity describes gravity and the large-scale structure of the universe. Quantum mechanics describes particles and forces at small scales. Both theories are incredibly successful. They have been tested countless times and have never failed. But they cannot both be entirely correct in their current forms because they contradict each other. General relativity treats space-time as smooth and continuous. Quantum mechanics says everything is discrete and uncertain. General relativity is deterministic. If you know the state of the universe now, you can calculate its state at any other time. Quantum mechanics is probabilistic. You can only calculate the probabilities of different outcomes. These are fundamentally different worldviews, and they clash when you try to apply both to the same situation, such as inside a black hole or at the Big Bang. A theory of quantum gravity would unify these two pillars of physics. It would give us a single consistent framework for understanding the universe at all scales, from the tiniest particles to the largest structures. It would be the culmination of a quest that has been ongoing since the early 20th century. And it would almost certainly reveal new physics, new phenomena we haven't even imagined. History shows that great unifications in physics lead to technological revolutions. When Maxwell unified electricity and magnetism in the 1860s, it led to radio, television, telecommunications, and all modern electronics. When quantum mechanics was developed in the early 20th century, it led to semiconductors, transistors, lasers, and computers. Every piece of modern technology relies on quantum mechanics. When Einstein developed relativity, it seemed abstract and impractical, but GPS satellites rely on relativistic corrections. Nuclear energy comes from Einstein's ERmc2 equation, showing that mass and energy are equivalent. A theory of quantum gravity could lead to technologies we can't even conceive of right now. If space-time is quantized, perhaps we could manipulate it. Perhaps we could create artificial gravity or control the flow of time. If wormholes can exist and be stabilized, perhaps we could use them for travel or communication. If the multiverse is real, and we could access other universes, the possibilities would be limitless. Now, all of this is wild speculation. We don't know if any of this is possible. Most physicists think it's probably not. The energy scales involved in manipulating space-time at the quantum level are so high that we may never be able to practically harness them. But the key point is we don't know, and history shows that understanding fundamental physics often leads to applications nobody predicted. More profoundly, understanding space-time would answer some of the deepest questions humans have ever asked. Where did the universe come from? What happened before the Big Bang? How will the universe end? What happens inside a black hole? Why does time flow in only one direction? Why are there 3 dimensions of space and 1 of time? Why do the laws of physics have the form they do? These questions have captivated humanity for millennia. Every culture has its origin myths, its stories of how the world began. Every religion grapples with the nature of time and existence. Philosophers have debated whether time is real or an illusion, whether the universe had a beginning or has always existed. For most of history, these questions belong to the realm of philosophy and religion. Science couldn't address them. But now, we are close. We have mathematical frameworks. We have the observational data. We have the theoretical tools that might allow us to answer these questions definitively. A quantum theory of gravity might tell us what happened at the Big Bang. It might describe the interiors of black holes. It might explain why time exists and why it flows forward. These are not just scientific questions. They are existential questions about the nature of reality itself. There's also something philosophically profound about space-time potentially not being fundamental. We experience space and time as the arena in which everything happens. Objects exist in space, events occur in time. Space and time seem to be the most basic features of reality. The idea that they might be emergent properties, that they might arise from something more fundamental, challenges our deepest intuitions about existence. It's akin to how we now know that solid matter is mostly empty space. When you touch a table, it feels solid. But the atoms making up the table are mostly empty space with tiny nuclei and electrons. Solidity is an emergent property of the electromagnetic forces between atoms. The table is not fundamentally solid. Solidity is an illusion that emerges at large scales. If space-time is emergent, then distance and duration might be illusions in the same way. At the deepest level, there might be no space or time at all. There might just be quantum information correlations between quantum bits, and space and time emerge from the pattern of those correlations. This would be a radical shift in how we think about reality. This also opens intriguing questions about time travel. If space-time is a fabric that can be bent and warped, could it be bent so much that it loops back on itself, allowing travel to the past? Einstein's equations permit solutions with closed time-like curves, CTCs, paths through space-time that loop back to their starting point in time. These solutions describe things like rotating black holes and certain wormhole configurations, but CTCs create paradoxes. The most famous is the grandfather paradox. If you travel back in time and prevent your grandfather from meeting your grandmother, you would never be born. But if you were never born, you couldn't travel back in time to prevent their meeting. It's a logical contradiction. Some physicists have proposed ways to resolve these paradoxes. Perhaps the universe conspires to prevent paradoxes. Events arrange themselves so that any attempt to change the past fails. You try to prevent your grandfather from meeting your grandmother, but you fail. Perhaps you are the one who introduces them. Perhaps free will is an illusion in time travel scenarios, and events are predetermined to be self-consistent. Or perhaps time travel creates parallel timelines. When you travel to the past, you create a new branch of reality. In the original timeline, your grandparents meet and you are born. In the new timeline you create, they don't meet, but that doesn't affect your existence because you came from the original timeline. This is the many worlds interpretation applied to time travel. Or perhaps time travel to the past is simply impossible. Perhaps the laws of physics prevent it at a fundamental level. Stephen Hawking proposed a chronology protection conjecture. He suggested that the laws of physics conspire to prevent closed time-like curves from forming. Whenever you try to create a time machine, quantum effects become important and destroy the path before it can close. We don't know which of these possibilities is true. We don't have a complete theory of quantum gravity that can tell us whether time travel is feasible. But the fact that Einstein's equations permit closed time-like curves suggests that space-time is stranger than we imagine. Time might not flow in an irreversible direction as we perceive. Past, present, and future might not be as distinct as we think. Understanding this could change not only physics, but also how we think about existence. It could alter our philosophical understanding of what it means for something to happen to be real. These are the kinds of questions that lie at the boundary between science and philosophy, and they are the questions that a true theory of quantum gravity might help us answer. There is also the search for life and intelligence elsewhere in the universe. If we better understood space-time, if we knew whether stable wormholes or warp drives were possible, it would transform our expectations for the future of civilization. If faster-than-light travel is impossible, then civilizations are confined to their star systems, or at best a few nearby stars. The universe would be filled with isolated civilizations, each evolving alone. But if shortcuts through space-time are possible, then the galaxy could be interconnected. Civilizations could meet, communicate, exchange ideas. We don't know which scenario is true. Physics as we understand it suggests that faster-than-light travel is impossible. But we cannot be certain until we have a complete theory of quantum gravity. There might be loopholes. There might be ways to manipulate space-time that we haven't yet discovered. Understanding space-time at its deepest level will tell us whether these possibilities exist, or whether we are forever bound by the speed of light. And finally, there is the sheer beauty of understanding. Humans have always looked up at the sky and wondered. We have built observatories, telescopes, particle accelerators, gravitational wave detectors, all to comprehend the cosmos. We have sent probes to other planets. We have photographed black holes. We have detected the cosmic microwave background. All of this is driven by curiosity, by the desire to know. The mystery of space-time is one of the last great frontiers. It's where our two best theories clash. It's the doorway to understanding the universe's beginning, the fate of matter in black holes, and perhaps the very nature of reality. Solving it would be one of the greatest intellectual achievements in human history. It would be a triumph comparable to Newton's laws of motion, Darwin's theory of evolution, or the discovery of DNA. We are living in a special moment. We are the first generation with the tools to seriously probe these questions. We have gravitational wave detectors that can measure ripples in space-time. We have telescopes that can image black holes. We have particle accelerators that can create conditions similar to the early universe. We have mathematical frameworks like string theory and loop quantum gravity that might describe quantum space-time. And we have brilliant physicists across the world tackling these problems. We might be on the verge of a breakthrough, or we might be decades or centuries away. Science doesn't advance on a schedule. Sometimes breakthroughs come quickly. Sometimes they take generations. But the fact that we are even asking these questions, that we are seriously trying to understand the fundamental nature of space and time, that in itself is remarkable. We are pushing the boundaries of human knowledge. We are trying to understand the universe at its deepest level. And even if we don't solve this mystery in our lifetime, the journey itself is worthwhile. So let's return to where we began. Spacetime Einstein's idea, the bedrock of modern physics. The framework that describes gravity, the expansion of the universe, black holes, gravitational waves, and the Big Bang. An idea tested thousands of times and never found wanting. An idea we use every day in GPS satellites in our understanding of the cosmos, in the technology all around us. And yet the fundamental mystery remains. We don't know what it's made of. We don't know if it's fundamental or emergent. We don't know what happened at the Big Bang when the equations predicted a singularity where physics broke down. We don't fully understand whether black holes preserve information or destroy it, though we are getting closer to an answer. We have equations that describe its behaviour, but we lack a complete theory that explains its true nature. This isn't a failure. This is where we stand. This is the frontier of human knowledge. Every great idea in science eventually reaches a boundary where it cannot go further without something new. Newton's laws reached that boundary when scientists started measuring the speed of light and the orbit of Mercury. Quantum mechanics and relativity reached that boundary when scientists started thinking about black holes and the Big Bang. And now we are at that boundary once again. We are at the place where the smooth space-time of Einstein's theory meets the quantum world of particles and uncertainty. Somewhere beyond that boundary lies the answer, a quantum theory of gravity, a description of space-time at the Planck scale, an understanding of what happened at the dawn of the universe, a resolution to the information paradox, perhaps a unified theory describing all forces and particles, perhaps a multiverse, perhaps something we haven't even imagined. The physicists working on these problems today are standing on a cliff looking out into the unknown. They are using mathematics and creativity and centuries of accumulated knowledge to build bridges across that gap. Some bridges will fail, some will lead nowhere, but one of them might reach the other side. And when it does, when someone finally figures out what space-time truly is, it will change everything. So the next time you use GPS or look at a black hole image or ponder the Big Bang, remember this. You are looking at one of the deepest mysteries in all of science. You are seeing evidence of something we use but don't fully understand. An idea that works perfectly in practice but remains enigmatic in principle. Space-time is real. We can measure it. We can photograph it. We can detect waves travelling through it. But we don't know what it is. And that's okay. That's where the adventure begins. That's where science happens. Not in the answers we have found, but in the questions we're still striving to answer. Einstein gave us the idea of space-time more than 100 years ago. It revolutionized physics. It explained gravity. It predicted black holes and gravitational waves and the expansion of the universe. It has been one of the most successful theories in the history of science. But Einstein himself would probably be the first to admit that it wasn't the end of the story. It wasn't the final answer. It was a step along the path. A beautiful, elegant, powerful step, but still just one step. The final answer awaits. It's out there in mathematics, in the experiments, in the observations yet to be made. Someone will find it. Perhaps in our lifetime, perhaps in the next generation, perhaps centuries from now, but it's there. And when we find it, we will look back at this moment. The moment when we knew that space-time existed but didn't know what it was. and we will see that it was the turning point, the moment just before everything changed. Thank you for joining me on this journey through space-time and its mysteries. Good night.